Good morning. This is Team 10 and today we'll be talking about exact differential equations. Now to begin with, we'll start by defining an exact differential equation. An exact differential equation exists if there is a function f of x comma y or the potential function such that dou f by dou x is equal to m x comma y and dou f by dou y is equal to n x comma y, which means that d of fx comma y is equal to m of x comma y dx plus n of x comma y dy. And thus the solution is then obtained as f of x comma y equals to c, where c is an integration constant. If we take partial derivative of m with respect to y and partial derivative of n with respect to x, and if both of those are equal, our equation is an exact differential equation. And the next step is to thus integrate the dx terms under one integral and the dy terms under another integral. We start by talking about the four rules of solving an exact differential equation. The first rule tells us that when an equation is of the form m x comma y dx plus n x comma y dy equals 0, and when the equation is either homogeneous or when both m and n are quadratic or higher degree polynomials, we take integrating factor as 1 by mx plus ny, which we thus multiply it to the given differential equation, which makes it exact. This is done because sometimes the structure of the differential equation is such that the terms are weighted by mx plus ny, and dividing by this expression balances the partial derivative condition. We start by taking an example where we group the dx terms together as m is equal to x square y minus 2xy square and n as minus x cube plus 3x square y. And thus we take the partial derivative of both and we see that they are not equal. Since this equation is homogeneous, we change this equation by multiplying it with the integrating factor 1 by mx plus ny, which is 1 by x square y square, and which is not equal to 0. After multiplying our integrating factor to the differential equation, we get a new set of dx and dy terms, which we again further partially differentiate. After partially differentiating the new set of dx and dy terms, we see that they are both equal. This tells that the equation is now exact and that we can now integrate the new set of dy and dx terms separately. Upon integrating these dx terms and dy terms, we get our solution. Thus, a solution to this equation is x by y plus log y cube by x square equals to c. The difference between mx plus ny and this rule, which is mx minus ny, depends on the algebraic structure of the differential equation and whichever balances the condition. Dou m by dou y is equal to dou n by dou x. Thus, we multiply the differential equation by 1 by mx minus ny to make it exact. Let us see an example of rule 2. Here again we club the m and the n terms together, and that is the dx and the dy terms together, where m is equal to y minus y square x and n is equal to x plus x square y. Now again, upon partially differentiating both of these terms, we see that they are not equal. Thus the equation is not exact. To make this equation exact, we take mx minus ny, which gives us minus 2x square y square. Therefore, the integrating factor is minus 1 by 2x square y square. We go on by multiplying an integrating factor to the equation and getting a new set of m1 and n1 terms. Our next step is to partially differentiate these m1 and n1 terms, and we see that both of these partial differentiations give us the same result. The equation is now exact and we can solve it further by integrating the m1 and n1 terms under separate integrals. Upon solving our given example, we see that our final answer turns out to be 1 by xy plus half log of x by y is equal to c. Start by talking about rule 3, where if the equation is not exact, it can be made exact by multiplying it with a function of x alone. If this expression depends on x alone, then an integrating factor exists which is a function of x and is found by taking the exponential of its integral. We move on to rule 4, which also is similar to rule 3, and here we multiply the integrating factor if it has functions of y alone so that the equation becomes exact. We start by taking a question and then taking the partial derivative of the dx terms and the partial derivative of the dy terms. And as we can see here, if we apply rule 3 and take dou n dou m by dou y minus dou n by dou x whole by m, we get 1, which is x to the power 0 and thus a function of x terms alone. We can further find our integrating factor by taking e to the power of integration dx. Thus, we multiply our integrating factor by the given equation to make it exact. This gives us a new set of dx and dy terms, which we again partially differentiate in order to find if it's exact or not. And as we can see, both of these terms are equal. And thus the equation is an exact differential equation. We further go on by integrating this equation into separate integrals. Upon solving this equation, we get our solution to be e to the power x into x square plus 2y square. Next, we'll take a similar question and then again find the partial derivative of the m terms and the partial derivative of the n terms, which we see are not equal. Thus, to make this equation exact, we apply rule number 4, which is dou n by dou x minus dou m by dou y by m, which we get to be 1 by y square. We multiply this integrating factor to our differential equation to get a new set of m1 and n1 terms. We then go on by partially differentiating these new terms to get 6x square y minus 2x by y square and 6x square y minus 2x by y square. Thus, the equation is exact and we can integrate our differential equation. Upon integrating and solving, we get our answer to be x square y square plus x square by y equals to c.